My name is Osowska-Kurczab. This is Szczerbiński, and we work at Allegro as research engineers in the machine learning research team. We both have experience with the academia. Jacek did his PhD at the Department of Chemistry at ETH Zurich, while I'm finishing my PhD at Warsaw University of Technology in the topic of AI in medicine. So the MLR team, which stands for Machine Learning Research, is a research lab operating at Allegro. So it's kind of an R&D department with a strong focus on research. We work on implementing deep learning and machine learning methods that help develop the Allegro platform. Today we would like to tell you about the landscape of retrieval research, which is applicable to, for example, search and recommendations. In the presentations, we will emphasize how Allegro handles retrieval on a large scale. So, what is Allegro? We are the largest e-commerce established in Europe. We have more than 20 million active customers that, compared to the real scale, half of the population of Poland actively uses Allegro. Despite this scale, we have a very high satisfaction rate of our customers, measured by so-called NPS. For Allegro, it reaches a value of almost 82%, and it is a spectacular result. We place ourselves somewhere between Netflix and Tesla, so it's quite a success. Where can you find artificial intelligence on Allegro? In surprising number of places. Machine learning primarily assists three areas. Firstly, findability. So machine learning models allow customers to find exactly what they want to buy in the shortest possible time. Secondly, management of product catalog. We organize Allegro so that every product is in the right place with full information about it. Lastly, support of customer service. We automate communication with customers to solve their problems immediately, even on Black Friday. So as you can see, there are a lot of models serving on production, and we wouldn't be able to cover them all today. Therefore, today, our focus point will be on the findability applications, search engine, recommendations, and visual search. So what can you expect from today's talk? Firstly, we will start with a brief definition of the retrieval task, cover the basic blocks of retrieval systems. Firstly, we will start with this brief introduction. Then we will jump into some practical applications, how retrieval in Allegro is solved from the perspective of our three services: search engine, recommendations, and visual search. And in each of these tasks, we will address the question how Allegro deals with the scale, whether it is a blessing or a curse. And at the end, we will summarize the talk and happily answer all of your questions. So let's start with the definition of the retrieval task. What is retrieval? We can paraphrase the verb to retrieve as to find, to recover, to extract, and it will include any task that involves searching a certain set of documents based on the user's query, or the context in which the user is located, and then returned a structured set of answers. We should make this collection as orderly as possible, so that the most relevant answers will be presented to the user as the first ones. So how to translate it into a system design? Usually there are two separate models. The query model, which focuses on processing the query to understand what the user is looking for. And the second model is the scoring function that will know how to compare the query with the documents and how to return the answer. So what types of challenges are unavoidable in retrieval? Firstly, a good definition of correct answer. Typically, there might be lots of relevant answers matching the query. So which one to show first? Secondly, we will often have a problem with strongly skewed data distributions. We can distinguish in this section two problems: long tail, which results from the fact that some query topics are substantial and therefore are well represented in our catalog, while some are more specialized and they happen to be underrepresented. So the second problem is cold start. Our document database is constantly changing. And in particular, new documents are coming constantly in. So they won't have much interactions in our system. Thirdly, when designing systems, it is really important to ensure the fairness and interpretability of our algorithm. Our suggested answers should be as diverse and as unbiased as possible. And lastly, the scale. We usually operate on huge sets of documents. They might be millions, hundreds of millions, or even billions of such documents. And the algorithm has to make use of all of those, of all database, of the whole knowledge. So you might ask yourself how machine learning fits into this landscape. So let's look at a very simplified timeline. We can distinguish two groups of algorithms: building systems based on interactions and on trainable representations. So in this former approach, we will build some strongly sparse interaction matrices, usually between users and documents, and then using some methods such as collaborative filtering or matrix factorization, try to find some similarities, some patterns between such interactions. Alternatively, we can focus more on similarity in self and try to train certain representations, so-called embeddings, that will capture the similarity between documents. So here, deep learning and in particular CMEs networks and metric learning will be very prevalent. Today we will mostly scope on the second approach, being trainable representations. So in this approach, we should train some model that we'll then use as a document encoder. Good encoder produces good embeddings, but what does it actually mean? So let's have a look at a simple example. On the left-hand side, we can see a visualization of a sample embedding space in 2 dimensions. Each point is one object from our document set. In terms of, let's call them mandatory requirements, what do we want to achieve in the end? The embedding space should fulfill 2 basic properties. Similar objects should be close together in this space, while these similar objects will be far apart. These properties must be somehow quantifiable. So therefore, to measure the similarity, we would need some function capable of computing the distance between some pairs of objects. Don't expect actually any fancy tools here. Usually we will, in large-scale retrieval, we will use some simple formulas straight from basic algebra course like L2 norm or dot product. So let's assume we already have an encoder able to produce reliable representations. We have a similarity function able to quantify the relationship between those objects. The last thing needed is an algorithmic solution to do the final search for answers. In practice, searching through sets of like millions of possible answers via some brute force approach is impossible to implement. Our document catalogs contain like millions, billions of items. The simple yet effective approach utilizes nearest neighbor search. So in retrieval, the whole process of answer generation is usually managed by so-called indexes, which implement whole strategy of candidate generation based on approximate nearest neighbor search. So this brings me to the next topic, which is the challenge of scale on Allegro platform. What does it mean that at Allegro we do retrieval in large scale? So let's have a look at some numbers. As I said earlier, our platform is used by more than 20 million active users. It translates to more than 20 million search queries daily. Our catalog is quite large. We have more than 250 million offers listed on the platform. So we can clearly see that the scale may be somewhat of a challenge. Besides the enormous amounts of data, we want to offer our customers pristine user experience. So it means that we have to provide continuity of services as well as very low response times, even as low as 120 milliseconds. So literally, the answer is expected in the blink of an eye. So have it all in mind. Let's take a look at 3 services that implement Retrieval at Allegro scale. So the first task covered today is the recommendation scenario. Why do we need recommendations? The answer is quite simple. We want to support our customers in their journey through our catalog, eventually trying to increase their engagement on the platform, leading to presumably increased transactions. So where can you find recommendations on Allegro? Almost everywhere, starting from the homepage, through some specific offer listings, shopping cart, search page, etc. So by recommendations, we usually understand this kind of a carousel with different items, encouraging users to check them out. A scenario of the recommendation depends on the landing page. For example, on the page displaying a certain product, we might want to recommend similar items to it. So what is a vanilla system architecture typically used in the recommendations? Usually, you should expect a 2-part model consisting of a candidate generation and ranking step. So looking at this top-down view, we can see that the input is some context of the query. Moreover, our system needs a constant access to information about our catalog. For example, some defined features, available offers at the moment, etc. So the first step, candidate generation, is designed to do a coarse search through the millions of offers and return up to a few hundreds of candidates for recommendations. We need to ensure that the algorithm is fast and lightweight. Secondly, we need to refine our answer in such a way that the first offers shown to the user are the most relevant. It is crucial because of the problem of position bias that is inevitable in e-commerce applications. This step must be as precise as possible, given the limits on the response time. So today we will mostly focus on the first part of the algorithm, the part responsible for generating candidates. You may wonder how, in the end, we work with such architecture. What can we prepare offline? Which blocks would be used online? So let's connect all of the dots that we already discussed. Given the online scenario, let's assume that there is a query that we want to recommend to. Firstly, we need to process it by an encoder that will return a representation of the query. Secondly, we need an index to do an approximate nearest neighbor search to retrieve a list of recommendations. In offline, we should prepare this encoder. So good representation is key. How can we essentially train such an encoder? Currently, the state-of-the-art in large-scale recommendations is the 2-tower deep neural networks model. It is so-called a hybrid system. If you recall this slide with this timeline, where I mentioned 2 main approaches based on interactions and on trainable representation. So 2-tower uses the best of both worlds, because we will describe our offers in the input only based on their features, so on their content representations. For example, title or price of the offer. But we will train the model on pairs of offers that had some interactions with each other in the past. For example, they were co-clicked, one after another. So the encoder itself doesn't need to be very complicated. On input, it expects certain chosen features of items, for example, title, category, price. Then each input is encoded with an embedding layer that usually is trained end-to-end. Lastly, we concatenate the lesser vectors and process them through a feed-forward network with several layers. Finally, we have to normalize the input, the output vectors, because we expect them to be comparable with each other by means of some simple mathematical formulas. What needs maybe a further explanation is the two-tower nature of the model. One of the towers is the tower of the context of our query. It will represent the current state to which we are recommending to. What will it accept as input? For example, the offer that the user is currently on, a representation of a user, or, for example, information about the user's active session. So the second tower is the tower that models our catalog. Typically, during training, we want to mimic clickstream. So the input will be the offer that the user clicked next. To be more precise, let's agree that the input of the model are two offers, a query, and the next clicked item. Thus, we defined a two-element learning sample. I've shown you the architecture of the encoder before, but since our input is composed of two offers that essentially are entities of the same type, why not share weights between those models, between those two towers? It will provide us with a little bit more stable training and general symmetry of our model. So in the end, our encoder, given a sample pair of items, generated two representations. Last thing to do before calculating the loss is quantifying the similarity. We will usually compare the items with a dot product. So that's two-tower architecture in a nutshell. Let's briefly discuss the optimization problem solved during the training. Surprisingly, recommendations are usually solved via classification paradigms, where our goal is to predict the next clicked item from the catalog. We will model this probability between two offers with a softmax function. How this softmax function is defined, with S being offers, V their corresponding embeddings, and gamma the scoring function. So as a loss function, we can use the simplest negative log likelihood. But actually, there is one major problem with this approach. How to compute the denominator of the softmax? Because this would require recalculating the probability coefficient across our multi-million catalog. And it is certainly infeasible. So there is a solution to this problem, the so-called negative sampling. We will approximate our full set with what we have easily available during training. For example, a single batch, which instead of tens of millions, hundreds of millions, will have up to thousands of elements. And for them, we can already conveniently compute the denominator. But you may wonder, isn't it possible to select those negatives in a better way? In-batch negatives will be rather simple for the model. So given that we find a well-performing mining algorithm, we might boost the overall performance of the model and make it more sensitive towards some intricacies in the data. In a few moments, Jacek will tell us a little bit more about the topic of negative sampling in the next part of the presentation about the visual search. So Jacek, the floor is yours.
Thank you, Ola. Hello. All right. Visual search. Searching with images. Magic. So who knows that feature? Raise your hand. 1, 2, 3, 4, 5. And so who's got the Allegro app installed on your phone? A bit more people. Good. Guys, homework to do. Okay, check it out. So let me show you how it works. Instead of typing the query in the search bar, you just take a picture of the thing that you want to buy, and there you go, you see it on the listing. So let's define the task, okay? Because you may think of search with images or of visual recommendations, okay, of visually similar products. So the task is that we have a query, which is a photo taken by the user, and we got to find offers that are similar to the given query. Ideally, we would like to find the same product that the one that was photographed by the user. And then if we see this product among the top 5 results on the listing, then we say we have a hit. So the metric is top 5 accuracy. Okay, so the architecture of the solution is somewhat similar to the one in recommendations, right? So we've got the query, which is an image here. Then we pass it through an encoder, which is typically a convolutional neural network. And then the encoder, essentially, it embeds the query, which means it transmits it from the space of images into the vector space of Allegro offer representations. And then the index finds the nearest neighbors, and that's what you see on the listing. So the heart of the problem is to train a good encoder. And the baseline approach would be to use something pre-trained, like a representation trained on ImageNet. And if you take that, then you already get 35% of top 5 accuracy. And that's not too bad for a baseline, right? But of course, we can do better, because we can train the model on Allegro images. So what we want to do is to teach the model what it means that 2 Allegro offers are similar. So the paradigm is metric learning, right? We want to teach the model to make like embeddings of the same offer close to each other and embeddings of different offers far away from each other. And like the canonical approach is to use the triplet loss. So let's see what's going on here, okay? We want to minimize the distance between the positive pair and maximize the distance in the negative pair, but not all the way along, okay? Up to a certain limit. So what we actually want is that a margin appears between the positives and the negatives. And then once the margin appears, then we don't reward further pushing the negatives further beyond the margin, so that the data points don't diffuse all the way to infinity. So seems easy, right? You take positives, like 2 images of the same offer at Allegro, and negatives, 2 images of 2 different offers. That's it. Well, actually, it's not that simple, both negatives and positives. So let's handle the negatives first. The thing is that if you teach the model to tell the difference between a toothbrush and a watch, it might have an issue with telling the difference between 2 different models of a toothbrush. So what we actually want are both easy and hard negatives. The easy negatives will determine the general direction of the gradient, while the hard negatives will give the model like sensitivity to the detail. So how do we get the hard negatives? Well, if you look at this image, this is like during the training, we got the positives and some of the negatives still fall within the margin. Then these are the hard ones. Okay, so we mine the hard negatives. All right, so if we train our search model on the encoder on Allegro images with hard negatives, then we already get 61% top 5 accuracy. That's much better, right? But of course, we can do even better, because the positive pairs can also be improved. What I mean is that if you just take any two images for any given offer at Allegro, then frequently there will be crap, right? So people will, you'll find photos with 2 different products on one image, or a detail, or a size chart, or just whatever comes to the mind of the merchant. If you drop those photos, then the performance of the model increases to 67%. That's great, but we can do even better. A major challenge for visual search is the domain shift. So what I mean is that the model is trained on Allegro images, which always have a white background, and the user queries the model with a photo on a realistic background. Okay, so we actually want to add that kind of photos to the training set, but we don't have them. So we got to make them. And it seems kind of easy, right? You just cut and paste onto a background. But actually, we were surprised to figure out that copy-pasting pictures onto backgrounds is quite a well-established research problem. So it turns out that it's really important how you smear the edges, blur, what kind of background you take, and so on. So finally, we decided for two methods like seamless clone and Gaussian blurring clone. And if you look at these images, well, a human can tell that's a photo montage, right? But it turns out that if you do it right, then for a deep learning model, that's good enough. But in order for that to be good enough, you also need to pick the right background. So we tried like natural scenes and uniform textures. And actually, the experiments have shown that the natural scenes tend to do more harm than good. The model seems to be confused by the presence of other objects in the scene. Okay, so we went for uniform textures. And after adding the synthetic positives to the data set, the performance of the model has increased to 70%. And that's pretty much the model that is working on production right now. But as you see, the performance differs very much between the departments. You may imagine fashion is kind of challenging because like you may have very similar photos of different products, right? Imagine two red dresses differing just by a detail. And the other way around, you may have very different photos of the same product, like the same dress on a model or lying on a couch. On the other hand, culture and entertainment is kind of easy because the title of the book is just written on the cover, right? Okay, so as you see, we have been adapting the model to subsequent departments. And right now it's working for the most of the selection on Allegro. But there are also domains where the machine learning model has to work and cover the entire selection from day one. And that's the case for text search, which is the main entry point for our clients. So let's define the problem. Oh, this has died. Excuse me. Good. Given a pool of results, we want to reorder them such that the most relevant offer appears at the top of the listing. Okay, we call this problem re-ranking, and the machine learning approach to solving it is called learning to rank. So you may, from a bird's eye view, you may expect a similar architecture like in recommendations. But just there's one major difference. In recommendations, the query is another offer at Allegro, or it's you, the user. While in text search, the query is any arbitrary phrase provided by the user, right? It's totally open set. So this requires a slightly different architecture. So the first step is like a traditional search engine, inverted index on tokens. So we draw from the entire pool of 250 million offers, and we retrieve a couple of offers that match the search phrase the best. And this search engine, it already uses one ML-based feature, which is called offer score, and it's a measure of offer quality, but it's computed statically. I mean, it's not dependent on the search phrase. And this is more or less how ranking used to work at Allegro like 5 years ago. And you know, it was okay, but I don't know if you remember, but personally, I used to switch to sorting by price. And over the last 5 years, we have added this one neural network that picks the 300 matching, top quality matching offers and reorders them. And this has brought 10% increase in NDCG. NDCG is like a metric. It's the most widespread metric that measures the utility of a listing. Okay? And NDCG is important because it correlates with the value of sales. Okay? So in our case, the 10% increase in NDCG has translated into 4% increase in gross merchandise value. And you may be thinking like, oh, come on, 4% over 5 years, what is that? Why not 40%? But let me tell you, the leadership of our company thinks about that in a quite different way. Because if you multiply those 4% by the value of sales at Allegro, you get quite a substantial number. So I would say that our management appreciates machine learning. And you get to feel it when you work at Allegro. All right, so we know NDCG is cool, but it has one big downside, which is that it's non-differentiable, because it's a discrete metric, it's based on clicks, and this means you cannot optimize it directly with gradient methods. So what do we do? Out of many, many solutions, I'll just cover two. One is that you can come up with another loss function, which is like a continuous version of NDCG, and it's differentiable. And our team has come up with that and implemented and published and so on. But in the end, this is not what we have running on production, because this was too expensive computationally to fit within the 50 milliseconds time regime. Okay, so what we ended up with is a pairwise loss. So think about it. Pairwise means quadratic complexity, but it's actually just 300 offers, so we're good. So what you see here is basically logistic loss that makes sure that the offers appear in the right order on the listing. And then this loss is weighted by this delta NDCG factor, which measures the impact of a given pair on the NDCG of the entire listing. Oh, okay, so we got the loss function, great. And we got the historical data, clicks. So we got to optimize the loss on the historical data. Let's design a model that can do that. The architecture is kind of similar to the two-tower model, right? So we pass the search phrase and the offer title through the same encoder and compute the similarity between the two. To that, we add all the handcrafted features, like the offer price, or whether the seller is a super seller, like length of the query and so on. We pass all of that through an MLP layer and get the score. So the score is like the prediction of the offer relevance by the model. Okay, so we do that for all the 300 pre-selected offers, and then we confront the scores with the clicks, and we compute the loss. So that's how we train. And now, how much data do we need for the training? And here, actually, it turns out that the size does matter. Because look, what you see here on the x-axis is the number of listings in the training set. And what you see on the y-axis is the modal variance, which means like a measure how well it generalizes. The smaller, the better. So specifically, this is the difference between NDCG on the validation set, held out from the training data, and NDCG on the test set, data from production. Okay, so what you see is that at a certain point, when you train the model on at least 10 million listings, then the model starts to generalize well. And that's a sweet moment, right? Because at Allegro, sometimes you just see deep learning starting to really work well thanks to the scale. Let's summarize. You can break down retrieval into 3 subproblems. First one is to define the similarity. In machine learning, similarity is defined in the training data, either clicks or by skillful composition of the training pairs, like in visual search. Secondly, you gotta generate the candidates, and here you compare the query with the pool of items. And a canonical example of that is the two-tower model in recommendations. The final step is to reorder the results according to the relevance, and the proxy for relevance is clicks. But that's not the end of the story. Of course, you can do retrieval much better, right? So that's why our team does research on topics like personalization of the search results and recommendations, and like use of reinforcement learning in that, and so on. But as Ola mentioned in the beginning, we don't just do retrieval at Allegro. We do many things in machine learning, ranging from NLP through multimodal models to robustness of machine learning models. It's like you can find anything you want. So who's behind all of that? We're a group of around 30 engineers in 7 cities, and the core of our work is making Allegro. And that's a cool thing, because there's this perk like the look mommy effect. So it's like you can just, hang out with your friends at a beer and show them on your phone, hey, look what I've done last week, and so on. It's super cool. And then machine learning works at Allegro because there's the data, and there's the infrastructure, and there are people. There's an army of people whose job is to make sure that you can focus on modeling. Okay, there are tech teams like developers, analysts, ML ops, data annotators, and so on. But most importantly, there's a business environment that actually stimulates machine learning research. Really. Like business owners come to you with problems where there's no off-the-shelf solution. And you gotta design something of your own. And if you come up with something brilliant, then of course you can publish and go to conferences and so on. So I would say that half of the papers published by our team come from production projects and the other half from pure research. And in principle, we are entitled to 20% of our working time for research, but frequently, if it's a good research project, it will frequently turn into a production project, and then it becomes more than 20%. All right, thank you very much. Please check out our blogs and podcasts and follow us on social media. And last but not least, if you want to join us, then we got good news for you. We're looking for basically everyone. Juniors, mids, seniors, leaders, and of course interns. So our sponsored booth is right over there. Come over, talk to us, solve the machine learning quiz, win attractive prizes, fame, eternal glory, and yeah, we're happy to talk to you. And now we're happy to take your questions.